Good morning, folks. How's lab 3? Mostly done. Done. That's a positive, I'd say. So any lingering questions on lab 3 or what the write-up should be or anything of that sort? Peter.
One of the, additional questions that we should have answered in our lab report, you asked us to describe how we performed.
Quiet down, please. Stop talking. Thank you. Yes?
Just one of the questions, how to describe how we performed the integration.
Uh-huh.
But I don't understand what integration really came into the lab 3.
So you're doing a Euler integration to update the position because you're using an approximation of that the new position is equal to the old position. So this is, if this is n, this is xn minus 1 plus delta t times a velocity, and that's a straight up Euler integration. That's an approximation of dx dt equals v, rewritten in discrete form. And it is possible to do a much better integration than that. That just happens to be the simplest to code. It would be more stable, for instance, if you used an implicit Euler integrator, which does a backward step rather than a forward step, or to use the Verlet algorithm, which is a little better than that. So if you used anything besides explicit Euler integration, you might want to talk about it. Otherwise, describe Euler integration. That is, by the way, E-U-L-E-R, not O-I-L-E-R. And so that's kind of a numerical methods technical detail. There was another question. Yes?
So for the lab report, does it matter if we incorporated, like, do you want us to write about our code that has like 30 balls in play, or can it be whatever amount as long as it's at least 30?
So you demoed some code, and why don't you talk about what you demoed? All right. What's the largest number of balls anybody's seen? I think I sent 390. That was you. Yeah, you were saying, oh, what?
I thought we only had 385.
I'm rounding, okay? So, any other questions on Lab 3? All right, let's go back to Lab 4. Remember Lab 4? Lab 4 started this week. And Lab 4 is a motor controller, which is a closed-loop motor controller. So there's going to be a sensor. So if we model this at a very high level, what we're going to have is some sort of motor that's being fed from some sort of controller, which you're going to write, the controller software. This is going to, of course, is going to then feed back through a sensor. So the output is really RPM. And we're going to feed this back through a IR sensor back to a summing junction. And we're going to compare this by addition, actually by subtraction. So this is a summing junction. We're going to negate the feedback input. And here we're going to apply the desired RPM. So there's going to be some control signal at the input that you're going to type from a keyboard, which is going to be the desired RPM. That's going to be the input, the difference between the desired RPM and the actual RPM is going to be applied to some controller, which then applies a pulse width modulated voltage to the motor, which then produces some number of RPM output. And this should be robust enough that say when you load the motor by putting your finger against the axle, the system should keep the same RPM, should keep the same speed. So the high level description of this is a feedback control system in which we're going to, by subtraction, detect the error and then try and minimize the error. Question is then how mathematically to do that, since you have to reduce it to code. And it would be a really good idea to know how the motor responds to different frequencies before we try and build the controller. Because what we're going to find is that this control function has to be more than just a gain. It's going to have to take a derivative and perhaps an integral to get the error down to the point where you can pass the requirements of the lab. But first, let me just refresh your mind on Bode plots. And so we're going to be drawing a whole bunch of these. Log F is always going to be the horizontal axis, and it'll be either a log amplitude or a phase shift. And we'll need both the amplitude and the phase shift. And I'm going to motivate this by saying we're going to solve the equation for a motor in just a minute. But what we're going to find is that a motor has a Bode plot that looks like this. And the asymptotic slope is -2 on a log-log plot, with some time constant 1 over Tm, where Tm is the time constant of the motor, which you would get by spinning this baby and watching it decay in time. Right. So you'd determine the time constant experimentally. And if the motor has an asymptotic slope of -2, what must the phase shift be at high frequencies? Do you remember this from some systems analysis thing? At high frequencies, at low frequencies, the phase shift is 0. At the time constant, we're going to have some phase shift. And we're going to go as high as a phase shift of -180 degrees and start at 0 at low frequencies. So a phase shift, so an asymptotic slope of -2 suggests that there's going to be a phase shift of 180 degrees at high frequencies. And we're going to motivate that in just a minute. So, and what we mean here now, what we mean by frequency here is going to be how fast are you changing the desired RPM? Are you changing the desired RPM slowly or quickly? Or in fact, are you asking for a step in the RPM? Which after all, because Fourier analysis is real, a step here means that you have a lot of high frequencies mixed in with low frequencies when you apply a step. And what we're going to find is, and I think you'll be able, sort of intuitively feel this, that if you vary the voltage across a motor slowly, it's going to speed up and slow down approximately in phase with how you're turning the voltage up and down. But if you turn up and down the voltage really fast, in fact faster than the time constant of the motor is going to stay at a constant speed or almost constant speed while you vary the voltage. And at some high enough frequency, the motor will be speeding up while you're dropping the voltage and will be slowing down while you're raising the voltage. That's what a phase shift of 180 degrees means here. That the direction of the voltage change is going to be opposite the direction of the speed change. This is true in general for lots of linear systems. To further motivate this, we can say, okay, if we go to high frequency and there's a phase shift of 180 degrees through the motor, 180 degrees turns a positive number into a negative number. And so when we feed this back, we're going to get an addition here rather than a subtraction. That's not good, because now the error is amplified rather than being suppressed. And what we'll find is that if you get a phase shift near 180 degrees, the system is going to oscillate and will never stabilize. But let's now go back and do some analysis. Oh, I guess we should say, all right, so this is a second order system. Who would like to draw me the Bode plot for an ideal integrator? Who feels brave today? Anybody? So, what's the gain of an ideal integrator at DC? How big is the output of an integrator that's been integrating DC forever? Big. In fact, it's infinite. So, so if we look at log A versus log F for an ideal integrator, it's got to start at infinite gain and drop forever with a slope of -1. Why is it -1? When you take the derivative or the integral of sine omega t, you get over, when you take the integral of this, you get a 1 over omega corresponding to a slope of -1. So, ideal integrator. Therefore, what must an ideal differentiator be? I saw the appropriate gesture. So the differentiator then is going to have a slope of +1, because as you go to higher and higher frequency, the slope gets larger and larger until at infinite frequency you have infinite slope. So the gain's got to go up with a slope of -1, a +1. Okay, enough on Bode plots then. To sort of warm your brain up, let's just solve a motor. So if we have a DC motor, there's two equations that have to be simultaneously met. One is a F equals ma type equation, a torque equation, which says that the torque of a motor is going to be given by some constant kT times the current. Let's make that lowercase current. But every motor is also a generator. So we're going to model a motor as a RLC circuit. We have some V applied. There's going to be some series resistance corresponding to the resistance of the windings and maybe some other stuff. There's an inductance corresponding to the inductance of a winding. And there's a back EMF, which is going to be given by a KE times the rate of change of the angular change of the motor, the speed of the motor. So the faster the motor is going, the higher the back EMF. So we need to solve this. And what we're going to do then is to rewrite this in a form that's more easily solvable. So we'll write F equals ma, or actually torque equals moment of inertia times the angular acceleration, as J theta double dot plus a dissipation term. This corresponds to friction, theta dot. And that's going to be equal to some K times I. And it turns out these K's have approximately the same value. So we're just going to call it K. And then we can write Kirchhoff's law, which says that L di dt plus R times I has got to be equal to V minus K times theta dot. And we just solve that mess. Substitute out, get rid of current. And we find the following, that the vector theta dot, so now this is a complex number, right? It's phase plus magnitude, that the ratio of the angular velocity to the voltage is given by K over large J times J omega plus B times L times J omega plus R plus K squared. So this is a second order transfer function, second order equation. Oh, this is the solution for a sine wave, of course, because really what we're doing is we're taking the Laplace transforms of this and then solving the Laplace transforms. And so we're looking for a sinusoidal solution. But this is true for any solution because of superposition in a linear system. So you can treat this as a general solution as long as superposition holds. And we find, first of all, there's a factor of omega squared in the denominator. That's the highest, that's the leading term of the denominator, which means that at high frequencies the system must drop off with a slope of -2. The response goes as 1 over omega squared. At low frequencies, the system is dominated by constants, and we get something that looks like this. And it turns out the shape is, as I said before, it looks like a low-pass filter with a second-order cutoff. And the phase shift, because it is a second-order system, does in fact go to 180 degrees. So we're going to treat this as some vector function we're going to call motor. And we are going to then ask, what function do we need to multiply this by? Going back now to C vector feeds motor vector, feeds the sensor, gets fed back. Well, let's say that C is just a scalar. It's just a constant. Then we're going to subtract we're going to have an error which decreases with increasing gain. Now let me try and motivate that. So if we call this the output here, this is some sort of input, and this error, then the output as a function of f, the frequency now, because this is we're solving for a sine wave, is going to be equal to C of f times motor of f times error signal. And we can do the substitution because error, after all, is equal to in minus out. And we can solve this and find out that out is equal to in times C times m over 1 plus C times m. You can't mess with the motor function. That's a fixed piece of the motor itself. But if you increase C to a large value so that C times m is much bigger than 1, then C times m over C times m goes to unity, and the output is exactly equal to the input. That says that if you specify, I want 1,000 RPM here, that is what you'll get out, as long as the gain is great enough. So that's easy. You just choose an infinite gain. But that doesn't work. First of all, we're working on finite systems, so you have to choose a finite gain with a finite voltage. And secondly, if you choose a really large gain, then at high frequencies, where the phase shift is 180 degrees, you'll be subtracting a really large negative, well, you hope it's a negative number, but in fact now it's become a positive number because of the 180 degree phase shift. And you'll get gigantic overshoots. You'll get changes in the wrong direction, which are very big. So merely increasing the size of C to lower the error doesn't work very well. But however, it is completely true that if C is a scalar value, a constant 10, that the larger you make C, the lower the static error. So you're going to have a dynamic here. You want to raise the gain of the system as much as possible to lower the error, and you're going to want to lower gain as much as possible to make it stable. What do you do? It's actually a little worse than I've said, because while the formal gain of the motor, the phase shift of the motor at high frequency is 180 degrees, there's actually a little more phase shift that your circuit is going to inject. And that is, you only know the position or the speed of at the last time a blade crossed the infrared. And until the next blade crosses the infrared, you have no information about the speed. Therefore, you effectively have an extra phase delay. You have a time delay your last estimate is obsolete as soon as it happens. Your last speed estimate is obsolete while you're trying to run the control loop. And that induces an effective phase shift which is speed dependent. The interesting thing is the system becomes more stable as it goes faster because you're making more measurements per second. And therefore the phase shift is smaller, the effective phase shift due to the time delay is smaller. That's one reason we're testing you above 500 RPM. So we're going to ask you to set the system to 500 RPM. We're going to ask you to step it to 1,000. There's all kinds of limits on the system. You can't go above 3,000 in any case because that's the maximum speed of your motor. You can't go below 0 because you're not allowed to reverse this motor. So staying in the range of 500 to 1,000 means that you have a high enough sample rate at low speed to get enough information to make the system stable, and you have enough headroom above 1,000 RPM to make the system moderately linear even when you do the step. So we're going to ask you to step it to 1,000, hold it for a while, drop it back to 500. And what we're going to ask you to record on the oscilloscope and show us is the response of this system as a function of time. And I would guess that a well-performing system is going to rise exponentially to a constant offset value and then decay exponentially with a slower time constant when you turn the power off. And as we'll see in a minute, since we can't apply negative power, you have only one power supply plus 12. Since you can't apply negative power to this motor, the only way it can slow down is passively. You turn it off and it passively turns itself off. So this is the passive time constant of the motor. It can speed up much faster if you give it a large voltage. If you turn up the gain enough, the static error will get smaller and smaller. Turning up the gain makes smaller error, higher gain, smaller error, static error. But if you turn it up too much, the system will come up really fast and keep going and overshoot. Notice that it's high, decay down, get below, get higher, and you'll end up with limit oscillations going from 0 power to full power as fast as the controller can, at the time constant of the motor. So very high gain means unstable system. So what's a person to do? Well, it's the phase shift that's messing us up here. The phase shift is too high at high frequencies. 180 degrees phase shift is enough that it destabilizes the system because it changes subtraction into an add. So let's get rid of some of the phase shift at high frequencies. So again, the motor has a response that looks something like this. So the motor has a response that drops off with a slope of -2 and therefore a phase shift of 180 degrees. What would happen if we multiplied this now? If we multiplied this by our new controller function, so now this is log of the controller function. What happens if we don't add any phase shift at low amplitude? So this is 0 phase shift, but right about where tau m cuts in, 1 over tau m, we start adding some phase shift. let's make a differentiator with a slope of +1. That whose differentiator cuts in at about the frequency that the motor starts to cut out. Now, instead of having a net slope, if we multiply these together, on a log scale, if we multiply a slope of -2 times a slope of +1, we get a slope of -1. So now the slope is -1, the phase shift is -90 degrees, everything's stable. If we do this, this is referred to as a proportional differential controller. So the proportional term is the, now I didn't draw the gain, this is, oh I did draw the gain. This shouldn't be 0 here, it should be the DC gain. So we have a gain of the system down here. This is the proportional term, and then the differential term is going to be set by the ratio of P over D, which is going to say when does the differential term become dominant and keep the phase shift bounded at -90 degrees. So that means that you have to implement a C of T and implement a C of T going back to the time domain, because after all that's where you're doing it. There's going to be some proportional constant times the error that you're going to get by the subtraction plus some differential coefficient which you're going to choose times d error dt. So your controller now is going to have two coefficients, a proportional term and a differential term. So what you might say is that you're going to have some P times error plus D times the error at times n times minus the error at time n plus n minus 1 all over delta t, where delta t now is going to be the rate at which your control loop is running. So this is the 1 over delta t is the rate of the control loop. And the derivative term should help with high frequency stability. Adding a little bit of differential term in, making a small d constant, will help stabilize the system at high frequency. High frequency? High frequencies are near an edge. Whenever you have an edge, whenever you have a step, you have high frequency input, right? Now, any questions? This is a really fast kind of go-through of all of control theory. Any questions so far? Another possibility is, now thinking sort of in the time domain, you've stepped the system, you have a constant error which is related to the gain. Is there a way of changing the controller even more so that the static gain isn't changed, P isn't changed, but this system notices that it has a little error and sort of incrementally gets closer to the right value through a different scheme. Yeah, right, it's exactly. So, and what you could think here is that you could add another term. So we have a PD term. What if we were to add an I in the center and call it a PID controller and give it an integral term that says we're going to take the integral of the error over time and make that 0. So we're going to do a control which is proportional to the integral, but there's some horrible technical details here. We have 10 minutes. Okay, we can do it. Oh yeah, first. So okay, now let's go ahead and do the integral. So the idea then would be to make a third term, an integral term, an I term, which is given by some I times the integral of error times dt. But we have to be careful here because we need to get the limits correct. So we're going to, and what we're going to find is that it is a bad idea to integrate forever because it's not too stable. The system tends to run to infinity. So what we're going to do is we're going to integrate with a lower time bound of the last time it crossed 0 error. So the bottom time bound is the last 0 error. And we're going to reset the integrator to some value. And then we're going to integrate up to the current time from the last 0 crossing, error 0 crossing. Logically, you'd say, well, all right, I'm going to reset this thing to 0. But it turns out that our controller is nonlinear enough. Now let me draw this slightly exaggerated here. Here's the desired control level. Here's the steady state. And then we start to integrate up. We integrate up. We cross. We reset the integrator. System decays down. Integrates up again. Decays down. Because we're resetting the integrator. What if we reset the integrator to 0.95 times its value when it crossed the value? So let's reset to 0.9 of the 0 crossing value. And that way, when we turn off the motor, it'll only drop 1/10 of the difference. We'll get a much smaller scallop. So then we're going, but there's even a, all right, so we're going to not reset to 0, but to 0.9 of whatever the value was when we crossed 0. And we need to do a little more work because we're going to find that, let me get over here, I guess. The system is only piecewise linear. And it's piecewise linear because we can't apply negative voltages. And so we're going to say that C of t is going to equal P times the error plus D times d error dt plus the integral of error dt if the error is greater than 0. Is greater than 0, and it's going to be equal to identically 0 if the error is less than or equal to 0. That says we can't slow the motor down actively. We just have to let it slow down because it has friction. So the system is a second order system when it's under drive, and it's a first order system when it's not under drive. It is piecewise linear. So as long as the error is greater than 0, then what you are going to have to implement is something that looks like C of t is going to be given by p times the error at time n plus d times the error at n minus the error at n minus 1 over dt, plus experience shows that if you let the integral grow without bound, bad things happen. So we're gonna do a nonlinear limit. We're gonna say we're gonna do the min of some I max, which you get to choose, but is the maximum allowable integral term. Min of I max and I times the sum from 0 crossing to n of n times dt. And the reset condition is going to be that we reset to approximately 0.9 of the 0 crossing value. And that's probably approximately what you're pretty close to what you're going to implement for lab 4. The best controllers I've seen control the RPM at 1,000 RPM plus or minus 4 RPM. So all errors from all sources are less than 4 RPM, which is amazingly good. I'm not sure I could do it. Students are clever. We're going to accept a rather larger range than that. But one of the things you're going to be graded on is how accurate is your controller? That being said, this is mostly a hardware project. The hard part of this is getting all of the hardware working at the same time, because you have a sensor, you have a serial circuit, which I don't think should be too much problem setting up. Has anybody set up the serial monitor? I know. Any problem setting it up? Just worked. Good to hear. You're going to have to hook up the sensor circuit. Oh, did we time out? Well, it says it's on. That's interesting. My. Okay, I won't show you. The sensor circuit consists of a light-emitting diode. The light-emitting diodes and the phototransistors are in one drawer marked IR. And you could tell them apart because the transistors appear black to the human eye because they only pass infrared. The photoemitters appear transparent because they pass any light out that they want to let out. And remember that the positive lead, The long lead is positive on the emitter and negative on the transistor. I wouldn't have done that, but then I didn't manufacture them. So think about this. You're going to have to implement it fairly soon. The arithmetic is not too hard. The logic is not very hard. There's basically there's two threads really. I don't know, did I recommend 3 threads? Yeah, there should be a thread. You want to isolate the thread which is waiting for keyboard input, because that's going to be running at human rate. Then there's going to be a thread which does the PID control loop, and a third thread that's going to update the LCD, because that has to go about 5 times a second, which is too slow for the control loop. If you put it in the control loop, it'll flicker a lot. You can't read it anyway that fast. Any last minute questions? First order for parts for the final project will be in about a week. So start thinking about what parts you want me to order. See you in lab.
Do we order parts through you or?